Hello, I'm Li Hao. The other day, I was talking with my colleague about TypeScript, about how we can improve our TypeScript. We use TypeScript day to day on our everyday work, but sometimes when we look at how library authors use TypeScript, it feels like it's another level, it's a different level where they use generics, they use conditional types, and use a lot of magical syntaxes that we have not seen or have a chance to really use our daily life. And we feel that there's a gap between an average TypeScript users and like advanced TypeScript masters. And we're thinking about how we can improve ourselves to reach the master level of TypeScript. So during the conversation, we found out that there's this site called Advent of TypeScript. They have a challenge, a 25 days challenge last year, end of 2023, which is like a similar idea of Advent of Code, where you solve daily challenges leading up to the Christmas Day. Looking at the challenges, we are like, maybe that's one way we can challenge ourselves and complete it, because it seems like a very interesting TypeScript puzzles. So I decided to give the puzzle a try. And as I progresses through the puzzles, I realized that, my God, the puzzles are very interesting, and I feel like I'm obliged to share with you guys about how I'm gonna solve them, because it's not just how I'm solving them. Even as I was stuck and I looked at the solutions, it's like opening a new door to me about how I look at TypeScript. So in this video, I will be going through the puzzles again from the beginning, one by one, every day. We'll walk through with everyone about my thought processes, about how I'm going to solve them. And I was thinking, how's the best way that you can get out of this video is probably you stop this video, pause it, go visit Advent of TypeScript. I'm going to paste a link in the description and go solve the puzzles together. You can solve the puzzle yourself, and then if you are stuck, come back and watch my walkthrough, or you see me stuck together and then we figure those things, figure it a way out together. Okay, so there we have it. Advent of TypeScript. Here we go. Yo! So this is the Advent of TypeScript. The link to this website is in the description, and we shall start at day 1. Gingerbread man, day 1. Okay, let's go. So this is Advent of TypeScript, where you can read through the questions over here, and this is where you write the type. I think Santa's favorite cookies is what we need to define. So right now it's unknown, and then here it's basically running some test case, right? So it makes sure that eventually, after we make changes over here, there's no more type errors. And here we still have type errors because the type that we're writing, Santa's favorite cookies, is not equal to what we're expecting, which is gingerbread or chocolate chip. Okay, so if we change this type to gingerbread and chocolate chip, now you can see that both types are equal right now, and then we have no more type errors. This shows a green tick, all tests has passed, and can hit submit. And that's it. We are done with day 1. That's easy, right? Okay, so we've done with day 1. We are moving to day 2. So it slowly progresses the difficulties. So in day 2, what we need to, instead of reading through, I guess we can actually just look at here and guess what we need, right? So here, basically you have the type called cookie survey input that takes in. So this is a generic, okay? Takes in this type, and then what it returns this type is it has to become like a union of different strings. And these strings are actually the keys of this map. So I guess what we can do is we can take in an object, right? And then we return the key of object. And I guess surprisingly, it passes all tests, right? So I guess that's it. So If you want to get the key of an object type, you pass key of. So let's move on to day 3. Okay, day 3. So now in day 3, we have a GIF wrapper type that has 3 different types. And then what it expects to return is an object that looks like this. A present that is based on the first type, from based on the second type, to based on the third type. Right? So if you're given with VS Code trash prime, present is first, from is the second, to is the third one. So how are we gonna go with that? So we have generics, and generics can have multiple arguments. So here we can have the first one is the present, second is the from, and third one is the to. And the present is basically this type, from is this one, and to is here. And voila, you see, we have passed all the tests. That's not too hard, right? I mean, it's doable. Let's go for next one. Let's go for day 4. Okay, I think day 4 is where it starts to get a little bit harder. Okay, so here, present delivery list, and mixed behavior list. So we are going to, what we need to do is that given this as an object, we're gonna return this as an object type, right? Given this type, I'm gonna return this type. So basically we're going to do a mapping, a map object literal. So we're gonna map. So the key is the same, but the value of the key, the type of the value of each key is mapped to something else. And how are you gonna write about this? Let me show you. So here we can have so let's take in an object as the generic, because here this one takes in an object. And then we return a mapped object literal, which looks like this. So first of all, you get a key. And what is the key? Well, the key basically is the key of object. So this basically loops through. So you basically create an object that the key of the new object type has the key of the same as the key of the original object type. And what is the value? The value is the type address. And that's how you're gonna map, create a new object literal type that is mapped based on the given object literal type. And that's it. We've passed all the tests, and that's it for day 4. Good job. Let's move on. So day 5 of type, advent of TypeScript. So now the next thing we need to do is that we're given a list of Santa list, given 2. Your generics have 2 arguments, and each of them are a constant tuple. It's a tuple type, fixed length, and then like it's like a read-only constant array, or you can think of it as like tuple or tuple. And now what we expect to return is a combination of like concatenation of that tuple or the read-only array. So how are we gonna do that? Well, you can give like this is like the bad and this is the good, right? We have 2 array types, and what we need to do is that we can do this to spread it out. But well, it has to be, if you want to spread it, this bad and this good has to be array type. And we can tell TypeScript that the argument, this generic argument, can be a subtype of a certain type, right? Basically, you can say that it extends from something, which translates to it is a subtype of a specific type. Right? What it means is that later on when you're gonna use center list, this type that you pass in has to be a type that is a subtype of the constraint that we can define. Right? And that constraint here, we want to make that constraint as this and this type has to be an array type. So I can say extends any. So we don't really care what is the content of the array, then we can say its type extends of any array. Now this doesn't satisfy this this constraint. I guess we need to make it a read-only array. Right? Read-only array. And voila. Now this types is a subtype of read-only array. So therefore now there's this constraint pass, and then because we know that now anything that's passed into bad and good has to be an array, we know for sure we can spread it, and therefore we just spread it, right? So that's it for this, and we hit submit, and we're done with day 5. Whoa, let's go for day 6. Let's go. Day 6, filtering the children. Okay, so now we are given basically we have 2 arguments for our generic. The first one is like a union type. The second one is like a string type. And what we need to do is we need to filter out this naughty from this type from the union, right? So if you have naughty, you have a nice union with naughty and naughty, you expect to return just nice. If you remove this from here, then you expect to just return like the string and number, right? So this is like omit, right? So you can actually write it this way, where this is like the union, and this is the to remove. And here we have the omit. Is it called omit or exclude? Union and to remove. And yeah, so exclude will exclude the type T from those that are assignable to U. What does it even mean? Well, but what it means is that you can exclude from the union type for whatever type. So union, you have 3 different types union together. So it will look at each of them and then exclude those that can be assigned to this type, which is in TypeScript way of saying that it's the same type, or the type extends from, like it's a subtype of what this type is, right? And in this case for strings, usually it just means that it has to be the exact string that matches. Okay, so we are done with day 6. Yes, good job with day 6. And so let's move on to day 7. Day 7, filtering the children. Okay, so now I guess it's like one step up because it says part 2. So what is the day 7 challenge, right? So we're given this an object literal type, and then the pan good is the type that we need to define, takes in a generic. So okay, so we're gonna say this is the object that we have. Okay, now what it returns, the type is it will add good underscore, like a prefix to each of the keys over here, right? So if you say don't play, then you say well prefix with good, don't, good, play, and the value is the same. Okay, so we're gonna use, remember the previous challenge where we do mapped object literal? We're gonna do the same thing here as well. So we're gonna say key is in key of object, and the value is basically object key, right? So object is this object type, and you can pass in the key to get the value. So it maps exactly what we have. So if you hover over here, you see that basically we have not changed much. We've taken the object and then we say for each of the key, the value type is the object key. So it's the same as what we had passed in. Okay, so but now we're gonna tweak a bit on this to define what is the key. And the way to define the key, we can change the key by saying as. Okay, so basically you have say this, the key is from you can because this is a map object literal, so you're gonna say the key is from the list of keys of the object, and then for each of the key that you just loop through, you can actually come up with a new type that is meant to be the type for the key. Okay, so here it's like you can map the key to something else. Here you can map the object to something, the value to something else, the type of the value to something else. Here we can map the type of the key to something else. And for key, what we are going to do is we're going to prefix good. So we're going to use the string template literal type. So here we're going to say good underscore and then key. The thing is that the key is not string. So we have to return we should only, because this object can be anything that for the key for object can be any type, can be a number, string, boolean, big integer, or whatnot, right? So we will have to say that only when it's string, then we do this mapping, because apparently TypeScript doesn't allow us to have a non-string value within a template literal. So what we're gonna do here is that we're gonna add one more. We're gonna do one more step, which is to check whether the key is a string. So if it's a string, then we do this. If it's not a string, then we say that actually we don't really care about the key. We can drop the key. Okay. So there's a if else. So we're gonna use the conditional types in TypeScript. So here we're gonna write, say, for example, I'm gonna make some space here so that you can see. First thing is we're gonna say key extends string. So if it's a string, then yes, we're gonna use this. Right? If it's not a string, we don't care about it. So we're gonna say never. Just whatever it is, it's never gonna happen. And whatever you can also specify never to drop the keys, because here the key can never be never, so whatever it turns into never, those keys will be dropped. So with this, we have now converted the key to prefix with good, and you can see our little tick marks tells us that all tests have passed. Haha, so smart. Let's hit submit and move on. Good job, you've completed the challenge. Let's go to day 8. Let's see what awaits for us. Okay, so now filtering your children, part 3. So here I'm going to remove naughty children from Santa's list. So Santa's list is an object. Okay, so we're going to say object as a generic argument. Immediately you can see that now we don't draw a red line over here, because now it does allow us to take a generic type. And now with this, whatever you pass in, you are going to remove any keys that is not that starts with naughty. Okay, anything that starts with naughty should be removed. Okay, so here we have don't cheat, naughty play fair. Naughty will be removed. So how are we going to do that? So same thing, we're going to do our mapped object literal. We have our key in key of object, and the value, I'm going to use object key. So now what we need is we need to transform the key. Remember the last puzzle when I say if you turn it into never, it will be dropped, right? If it's so we're gonna have a conditional that says that if it starts with naughty and something, then we're gonna drop it. by turning it into never. And if it's not, then we're gonna keep the key. So basically the value should be the same. So let's see. So we're gonna say the key extends something, okay? And if it's, I'm gonna say this first, naughty Tom. And if it extends naughty Tom, okay, sorry, let me type an S. As key extends naughty Tom, then we're gonna say never. So basically this is gonna drop the key. And if it's not that, then we're gonna say key, which is basically just keep the same key value for this key. If I save this, you can see that now what it returns is an object that removes naughty Tom. But we still have naughty trash and naughty candles. So how do we remove all of them? Or how do we determine whether something starts with naughty? Well, you can write, you can use template literal, and you can write it this way, where it says that this is naughty, starts with naughty, and then whatever next is like you have strings over here, okay, whatever string, but it has to start with naughty underscore. And that's how you check for whether this prefix starts with naughty underscore. You can also have something where it ends like this, right? Naughty, naughty. So it ends with underscore naughty. But in our case, it's prefix, so we're gonna do it here like this. And hey, you see, we have passed all the tests. This little green check mark. I'm gonna hit submit, and that's it for part 3. So let's move to next challenge, day 9. So day 9, we have this type called reverse. And I guess by the name itself, we can tell that we have to reverse something. And it's reversing strings. Okay, so this is dasher, right? Reverse is this. This is, I guess it's dancer, dancer. So anything being passed to, we are going to reverse it out. So here, first of all, the reverse is that this is a string and it extends type string, okay? And now we need to reverse the string. And how are we gonna do that? Well, we're gonna recursively define the type, and we're gonna use conditional types. Well, conditional types is just perfect for this one because it allows us to extract certain things out of this string type. Well, what do you mean by extract? How do you extract certain things? Well, with conditional types, you can say that, say for example, I have string extends, say it has to be some sort of string, right? Say for example, it is REHASA, and then I don't know what's the last character. I can actually say that this is any string, right? And then and if I say this is 1, this is 2, then you can see that what I get is this string extends this. Yes, it starts with this prefix, right? So it gives me the type 1. So this is the type 1. Test 0 is actually type 1, right, instead of type 2. And this doesn't start with that, so this is type 2. Okay. So one more thing that a conditional type allows us to do is that instead of just saying that this has to be string, we can actually infer the value from here. We can let TypeScript to infer. So say infer, and this I'm gonna say maybe give it a variable name, infer C. So I'm gonna say C. So from here, you can infer if it's this matches this type. Just infer the value of C. Let me know what is C, and I say let me know what is the value of C, and then I'm going to use the type C over here. So C is a type, but I have no idea what the type is, and let me know what it is, and then I'm going to return it from here. So you can see that if it matches this, it returns C. And if I hover over here to look at the type, you can say it infers and it knows that it is D. It's a capital D. It can extract this information out. So we can use this to basically try to create a new to create a type, right? So we can actually infer, say for example, this is the first character, and we have no idea what it is, but we can infer first character, and then this we can infer the rest of it. And what we can do is that we can so this one is, we can say that we have the rest and first character. Oops. So here, if I hover over, you can see that now the first character is R, and R has been moved to the back. Okay, I have able to infer and put R at the back. So what I need to actually do is then for the rest, we can actually instead of passing rest, we're gonna use reverse type over here, since reverse allows us to reverse a string. And let's do that. And now we have a 2. Okay, 2. So here what we need to do is that here we're gonna just return a empty string, right? So as long as a string doesn't match this type, then what we need here is that we just return an empty string, because you can't infer what is the first, and it doesn't have like too many characters to infer for anymore, like, which means it doesn't have enough characters to do so. So when it doesn't match, I'm gonna say this returns empty string. And here you go, we have a recursive type based on conditional types, and we can reverse a string in TypeScript. Can you imagine that? Oh my. And see, we get all our tests passed, and let's submit. And good job, we have completed this challenge. So we have completed 9 puzzles in one go, and it's like easy. Let's move on to the next one, day 10. Let's see what awaits us as day 10. Hopefully it's not too hard. Okay, so here we have a street suffix tester, Candy Cane Way, and what we need to return is type true. It has to test whether it has a suffix of way over here. Right, so Sugar Lane Drive, it should return false. I mean, this is not too hard, considering the fact that we've just solved the 9, right? We can check whether this extends this string, or whether this string extends a string that ends with this way. And if it's true, then we can say we will use a conditional type, and say if it's true, we return the type true. If it's false, return the type false. So here, this takes 2 generic arguments. We're gonna call the first one string, and second one the suffix. And basically, we're gonna say if a string extends any string, right? This is any string that ends with this suffix. I'm gonna say this is true, or else it's false. Well, TypeScript complains that suffix, you pass it in the template literals, but I have no idea what suffix is. Can be a string, number, big int, boolean, and all these things, right? So, well, I'm gonna give TypeScript some hint. This can only be a subtype of string. Okay, this can only be subtypes of string. And here we go. We have said that if the string is any string and have the ends with suffix, we're gonna true, and this is false. And see, here we go, we have all the tests passed, and let's hit submit. And good job, we've just completed this challenge, and we have done the first 10 challenge. Wanna take a rest? If not, let's move on. Day 11, let's go. Day 11, let's go. Protect the list. Okay, so we are given this center list protector, and this would give us takes in an object, and it should return an object where everything is read only. Okay, so how shall we write this? Let's see, if I'm gonna have an object, I'm gonna make it read-only object. Does it work? Yes, it does work, but it is not recursive. See, it turns this, the first level, to read-only, but the inner objects are not read-only. Inner ones are still like this, but what we expect is all levels down are read-only. So what can we do here? Well, I guess we can have something like, our mapped object literal, where we go every level deep, and then we turn each of them as read-only. So here, of course, object, only when it's objects, then we do recursive. We don't wanna do a map object literals if it's not type object. So I'm gonna say object extends with like this. If it looks like an object, then I'm gonna have the object map literal, or else I'm gonna keep object. So here I'm gonna map it. So let's say key in key of object, and what is the value? It is object key, but we are also gonna protect it, so I'm gonna wrap it with center list protector like this. Let's see whether this helps. Let's see what is not working. Seems like Elliot is okay. I think first of all, Hacksaw somehow turns into a read-only with an object. So we need to check whether it's in function. If it's function, then we shouldn't do. So it's like object extends like a function. Then we just keep it the same. Don't do the read-only. And then else, if it's object, then we do the read-only. Let's see whether this helps. Seems like we shouldn't have read-only for functions. Okay, so somehow this read-only function, read-only boolean. In that case, I guess we can do we move this out. And if it's read-only, if it's object, then it's read-only with this object mapping. Something like this. If it's a function, an object. If it's object, if it's function, just pass as is. If it's a subset of objects, then we're gonna do a read-only where it's recursive, and everything else we still keep it as objects. And I guess we get our little green tick. I think that's it. I'm gonna submit, and good job. We have completed day 11. So we are going to move on next. I'm going to quickly pick at some of the solutions and see whether someone has any interesting way of solving. Okay. So this one, I think it's pretty similar, but it checks for all sorts of things like string, null, number, undefined, function, and all this. It takes with T. Also, we do our object literal. But I think one thing different is here that instead of using read-only, we can actually make the key read-only by adding a read-only modifier on over here. This works as well, and I think it looks the same as what we have. Let's see whether I think we are almost on the same line of thoughts. So we are done with day 11. Let's move on to day 12. Day 12. So find center. So we are given an array as a type, and find center should return us the index of where center is. Oh my god. Is this like an index of but for a TypeScript? So here, index of find center. We have to return 1. This one will return us 2. This one will return 3. And if it's not, then we're gonna return never. Okay. So how are we gonna solve this? Because first of all, find center, this is a generic type, right? Array. Okay. And let's say it extends something, array type. So how are we going to solve this? Okay, so first of all, let's break this down. First thing is we're gonna use the conditional type. Of course, again, we're gonna infer something, we're gonna extract something from this array. And then hopefully we extract the first element, for example, and see whether that is a center. If it's center, then I guess we found our center. But if it's not, then we need to keep finding where is our center. Right? So here, what we can do is we can say array extends this one, infer first element, and then also infer the rest. So the rest has to be spreaded like this. Okay. And if it's so we have to do something here. But if it doesn't fit something like this, then basically what that tells us is that this probably it's not array or whatever we are going to find, it's not here. So we're going to return never. Okay. So what is here? So what is here is that if first extends this Mr. Center clause, then I think we found it, right? We find this is the first one, so it should be 0. And if not, then there should be something else, like keep looking. And now if you look here, this one has already returned us type 0 because we've inferred the first one, infer the rest, and then the first is the center clause and it returns type 0. And if not, we have to keep looking. And keep looking, what we can do is, of course, recursively find center with the rest, right? You can keep trying with the rest. And if we're gonna just do it like this, one thing for sure is that the second item, yes, we can find center again, and then, but that means that we need to know that which levels we are in, and here we are at 0, and we need to increment something so that later on it's like 1, right? So we have to call this find center with something that is probably like something like 0 plus 1, and then we go every level deep, and then we increment by 1 every level that we go into find center, so that we can return that value here, right? So this is most likely like this is like return like a value, and then return this value over here where it starts with like 0, right? So here we probably want something like value plus 1, right? But value plus 1, this is not valid TypeScript, right? We can't actually write this, so we have to come up with some smart, witty way to work around this so that it works. Okay, so here the default value is 0, so if you don't pass value, it's 0. So here we still we are not, TypeScript will not complain if you don't pass it in, and you can pass value plus 1 like this. But we can't do plus 1. Okay, we have to come out with some workarounds. So one of the workarounds that you can do to increment something, well, one way that I've think about, and one way we can actually do, is actually to have it as an array. And so I wouldn't call it value, but like I guess let's keep it as value first. And then what we can do here is that to increment by 1, we can add a new item to array. Okay, so extends. Like why array? Well, what you can do with array, especially it's if the length of the array it's kind of like fixed. It's known during the like it's not dynamic. It's something like a tuple or something where TypeScript can able to know the length of the array. We can actually get the length of the array out like this over here. And then if it starts with an empty array, TypeScript knows that this value length is 0. And we do something like this where it's like type A equals to like array with one item. If you ask like type B equals to A length, TypeScript actually knows that this is length 1. Okay, if the array it's constant and it's known ahead of time like this, it knows it's length 2. So this is a way that we can like a cheat that we can increment something. So we keep an empty array and then we increment by adding one item, one element into the array, and therefore we can increment by once every recursive like types, and therefore we can find our length. We can get this value out, and then we know where the index of the center. And as you can see here, we get our green tick. We have passed all the tests, and let's submit. And we did a good job. So we've cleared day 12. Shall we move on to day 13? Let's go, day 13. So we are at day 13 now. We are at this day counter. Okay, it looks scary, but what is this? Okay, so here, day counter takes in two generic arguments. And what it needs to return is something like look like this, where basically it's a enum from 1 to 2, 2, 3, 4, 5, 6, 7. Union, sorry, not enum, union of the number 1 to 12, like this. Okay, so it's like so we need to turn this into a union of numbers from the starting to the ending value, right? So it's 1 to 25, then we have to create a union that looks like this. So how should we start with this one? Let's see. One thing we can do, first of all, if we want to create a number, in the last challenge we've seen is that we can use an array and then get the length of an array. We can get the length of an array. So basically, if we have an array of length 12, we can remove one item and then we can basically get the length, which is 11, right? Then we get the value 11. That could be one way. Let's try an idea first. Let's first think about how we can create an array that is length 12, like 12 items inside. Right? One way is that maybe I can say array, create array, and given this is like the length extends number. What we can do is first of all, we need to have a variable, right? We have to store the array that we're gonna create, and or something like that, right? So I guess it's like something like if it's a recursive, a conditional type where it length is the array length of len. If so, then return the array. If not, keep appending to the array, right? But the thing is, we need the array, the type array. Well, and so so what we can do here is actually, since create array takes this one, and we can actually you see here length, basically we just create a new type out of this generic. We can actually create multiple like variables in our recursive or in our generic type. We can actually create like variable types, like creating new types by adding this types over here, like in part as part of the generic. Say for example results extends array any, right? And to make it like such that you don't have to pass in, you can have a default value or initial value. As you can see, this is the initial value of the result that looks like this. So what we can do is that if results, so we check the length of the length, right? So if result length extends length, so basically if the length of the array is the same as this one, then we're gonna return this array. If not, we're gonna create array, and basically we keep length and then we get results. But we can't do this without appending item, then it will be just endless recursive loop. So we're gonna say spread this one and then add like maybe like one value. Like for now we just create empty string. So here let's say I have a type arr array equals create array 5. You can see that this array now has 5 items, right? 0, 1, 2, 3, 4, 5. So what we can do is then we can create we can use this and then we can get numbers out of arrays, right? So actually one thing I suddenly think of that we can do is that instead of appending empty string, we can actually append the result length over here like this, right? So one particular thing that you can get out of this is that now array will be type 0, 1, 2, 3, 4, right? And why we want to do this 0, 1, 2, 3, 4 is actually we can extract all these elements out as a union type because this is an array type, and if we do something like number like this, what we get out is a union of all the elements, right? So this is an index type where you could index, like say I need a type that is inside the array, and a number is just any number, right? So it will be union of each of the element. So if I specific number like 3, then I get like the third item or the fourth item, right? But if I just put number, then it will get all the elements. But getting all elements in TypeScript means getting a union type of all the elements, right? So actually we can get 0, 1, 2, 3, 4 out of this create array. So what we can do here actually now is that if the day counter is like a starting and ending, what we can have is create array the start like number. Okay, so this one has to extends number. So create array. Does it work? Somehow it doesn't work like this. But it's okay. I think we can put like number over here like this. Then this one gives us basically this gives us if it's 5, then it gives us 0, 1, 2, 3, 4, right? And if it's and we can actually have like the starting, like say this is 1 and this is 12, array 2. So this one gives us 0, this one gives us 0, 1, 2, 3, 0 all the way to 11. And what we need is we need to remove 0, right? Basically remove the common ones. Like if it starts for 4 to 12, this have 0, 1, 2, 3. This one has 0, 1, 2, 3, 4, 5, 11. And what I need to do is I need to remove from here, remove everything from here, right? And that is our exclude. So So I have to create array with the ending. Why I call end? Start and end. Start and end. And then we include one more, which is the end, because we don't have the last element. So here we have day counter, right? And see, I have 1 to 12, and this one gives us 1 to 25. And if I can do something like a equals day counter 5 to 10, this gives me 5, 6, 7, 8, 9, 10. So here we have to count the days by using arrays to create length, to create value, and then to extract the element. And then we do a witty thing is that in the array, instead of appending like empty strings or appending like useless elements into the array, we append length of the array into the array itself. So in that case, the element of the array actually has all the values that we need, and then to extract all the values of the elements as a union, we use the index type to extract it out, and therefore we basically can create a union of like all the elements that we need. And because we have a start and an end, what we do is we're gonna exclude whatever like from 0 all the way to the starting, from the 0 all the way to the ending, right? And then of course we need to add the end, because the length, if the array is length 11, the index that we get, the value that we get is 11. The most is 11, right? So if it's length 12, then the most we get is 11, because this is right before we add this is right before the length of the result is equal to the length of what we need, right? So this is always a length minus 1 over here. That's it. Let's hit submit, and good job. We have completed day 13, and let's move to day 14. 1-4. Let's go. Go. Okay, so we are at day 14, the naughty list decipher. Okay, so what we need to do is we need to, I guess, split the string by slashes. Okay, so and then we turn them into unions. Okay, so Timmy, Jimmy with a slash, then you have Jimmy, Timmy as union. If Elliot without slash, then Elliot is the results. And here we have Melky, Prime, Theo, Trash. And then we split by slashes. So how do you extract this by slash? Well, remember our good old conditional types, and we use infer to infer something else. And that is exactly what we are gonna do. Right? So first of all, this is the string extends string. Okay, so here, if our string extends something like here, name, infer name, infer rest of the string, then we get, if it's like this, then we get the we need to have to recursively decipher the rest of the string, or else we get the name as the return, right? Oh no, sorry, this one returns the string, and whatever we decipher with the rest of the string, this unions with the name. I think that's it. Wait, I still don't get the spelling is wrong. Okay, and that's it. We've got it, right? So here we basically try to use infer to extract the name if there is, and then rest. And if the string doesn't look like this, then it's most likely like something like Elliot, where the whole thing is the name. So I just return the string itself. And if we can decipher something like this, then we're gonna recursively decipher the rest. and then union with the name that we just extract. And that's it for day 14. It's an easy one compared to last, like day 13. And we shall move forward to day 15. 1-5. Let's go. Day 15. Box toy. Okay, so box toys. Basic. Now we have this generic type, and we are given like doll, and then we given like 1. Then basically we create an array that has 1 element. And if it's something like this, we have 3 and 4, we're going to create an array of 3 elements and 4 elements. Okay, that's tough. Let's see what we can do. So for 3, I think let's create a type that we can use to recursively create an array, right? We just create an array based on 1. Okay, so we're gonna say type create array. This is the value, is a string, and then the length extends number. And I think we have seen how we can do it the last time, right? Where we recursively creates the length, the array to match the length of length, right? So what we do is that we check first. We need an array, and that array we can tuck it in here like array extends any, starts with empty array. So this array length, if it's already equals to length, then we return this array. And if it's not, then we are going to create array with v length. This is the same, but when we do recursive, we want to keep building up. So this is where we build up the array, and the item is v, right? So v pass it here. So this should gives us an array of length where all the elements is v. So box toys, where we have the v, the value, extends string, length. What we need to do is that we will extend number. What we do is we will call create array value with length. Right? Is it? Okay, so here what we get is only the okay, so the 3, 4 is a union, and we need to map union. We need to call this create array for each of the unions. Let's see how we can do that. Okay, and the reason why it doesn't work with our current solution is that if array length, right, that we build up extends 3 and 4, basically it's saying like if 3 extends 3 or 4, right? And of course it's true, because 3 can be assigned to type 3 or 4, the union, right? So of course it will just returns a length of 3, but not like creating 2 arrays. So you need to create 2 arrays for each of the union type. So we need to have some way to split this into separate like separate type, separate element, or something like that. And let's see. So if I try to create an object like a equals to length, right? What I get is still this is a equals 3, 4. Okay, so this is a bit annoying. We need to have a way to split this into 2 different things. And speaking about objects, one way we could do is, remember that when we do a mapped object literal, where it looks something like type A. Say for example, this is A equals 1, B equals 2. What we do is type the mapped object is key in key of A, and then we'll do something to map over the value, right? And you get A and B. And key of is actually A or B, right? Key type C equals key of A is actually a union. Okay, it doesn't show, but it's actually a union between of all the key values. So I feel like we can make advantage of this by creating an object that splits this thing into two separate properties, and then we'll figure out how we extract the values out, right? So here, for example, here we have key extends key in length, and what we can have is create array v value and length key. Right, so let's see what we get now. It's basically we have, okay, so this one is 1 with a doll, and this one is 3 with 3 items, 4 with 4 items. So basically we have already split out the union type into 2 separate properties, and now the goal that we need to do is basically to extract these 2 out from the as union. All right, and union of the values is basically like a value type, or you can say like this is like maybe like a number. Can we do that, or any, right? Does it work? Oh no. Okay, maybe length, right? So basically this will give us an access of what is the value, right? And if I pass 3 like this, then this one will give us the value where the property is 3. And this, if I do 4, then this gives me a value property which is 4. And I need 3 and 4, right? Basically that's, I will give us the value union of the value of 3 or 4. And what I can do is specify length, right? This gives me all the values in union. And I guess that's it. We get our green little tick here. All tests have passed. And hit submit. And we have done a good job for day 15. So let's move on, shall we? To day 16. 1-6. So day 16, okay, it looks scary right now. I can see this and it looks scary to me. Okay, so day 16 is to find Santa. Okay, we need to find where Santa is. And by the looks of this one, I assume this is to find the coordinate, right? So it's 0, 0. Let's see whether it's true. So find Santa, forest 1. This gives us 3, 1. Okay, so this is like the third row and the first element. Okay. So this one is 2, 2 because so we are going to find the coordinates of Santa. Okay. So let's see how we can write this. So first of all, it takes in the map is actually array of arrays, and we need to find where Santa is. How should I? How can I do this? Let's see. I think first of all is to find the rows, right? Find the rows. To find the rows, let's see. I think one thing we can do is, again, we can use something, we can rely on something that is the object, mapped object literal, right? Oh wait, this sounds very familiar with our solution that we did for the find index. Remember when we do find index, when we find Santa? I think that was also find Santa, but that's like part 1. where the find index is like one dimension array, where we basically have an index over is it index? No, we weren't using index, but we use something like, okay, let me try to recall. So we have something like find center array, right? Okay, this is find center 1. And basically what I say is we maybe use, okay, this is one, we use conditional type to infer. So here extends, infer the first one and infer the rest, right? And if we able to, if first extends the center clause, then we need to return something like 0. And if it's not, then we're gonna keep finding, like find center 1 with the rest, right? And if it doesn't look like this, then we're gonna say no, we can't find the center clause, right? And then we can't keep returning 0. We say we're gonna keep something like like index, and the index is actually something like an array because we can't keep numbers. We can't increment index plus 1. So we say this is a array. And here when we increment is like index, we use the spread to create one more element, and then the result is index length, right? So we use length to store the variable. Instead of 0, 1, and then 1, the index plus 1, we use an empty array and then add items into the array and then use that length of the array to extract the value out. And I guess we can write something similar here for 2D arrays. We can have column extends any. We can have row. Right? And what we can have next is find center. Sorry, let's see. I think instead of inferring and then finding next, right? I think we can write it slightly differently. We can write it this way, right? So instead of like doing the infer and find, right? Actually, one way that we can find center. Let me try to write this first. A equals find center, like maybe like this one, right? So this gives us like 1, right? So instead of like, okay, so instead of doing this, right, what I want to propose is, instead of inferring the first element and using extends, I'm gonna go straight and say array index length extends the center clause. And if it's so, then I guess index length is the result. If not, find center with with this one, right? And then let's see, it says it's in excessively deep and possible infinite. Oh, okay, so there's no rest. Okay, that's arrays here. And then so here we still get 1. Instead of splitting the array, inferring the first item and the rest of the elements, we can actually read directly based on the index that we just incremented and then find the value of that and see whether it extends center clause and then return it as a value. Right, so we can do that same with the column and row here for finding the map, right? So if the map where the column length and the row length extends center clause, then the return value is this, right? The column and the row. And if not, then we are going to find center by incrementing column and incrementing row. Of course, that is not correct, right? If you increment a column and incrementing row together at the same time, what you would end up is that you were just finding like the diagonals, right? So I would say like we can increment the row first. Okay, we increment the row first, and once the row reach like 0, 1, 2, 3, 0, 1, 2, 3. Okay, if the row reach the end of like reach 4, then we actually need to resets the row and then increment the column. So what we can do here is that if the row length extends the map 0 length, right? If the row length has exceeded it's the same as the length, then what we actually need is find center map where we increment the column, and then we start with empty for the row, and if not, then we will just keep the column and then just increment row for now, right? So I guess that's it. Recursive search, iterative search with recursive type definition, and you can see we have our little green tick says all our tests has passed. So let's hit submit, and we do a good job. Yay, we have solved day 16 and we are moving to day 17. Let's see what awaits for us in day 17. So day 17, who wins? Okay, so it's like rock, paper, scissors. It is rock, paper, scissors. And then you will say the second guy win if it's win, right? If it's the second guy can win the first guy, then it's win. Second guy can, if the second guy will lose to the first guy, then will lose, or else will be a draw. Okay, and then basically there's not much combination. Actually, we can hard code all of them, but we wouldn't want to hard code all of them, right? So I guess one way we can do is that first is that who wins takes in player 1 and player 2, and if player 1 extends player 2, then we know for sure is draw, or else we need to figure out something, right? So for draw case, we already know that it's draw. Now to know who wins, we have to define something, right, somewhere, and we can actually define a win map. In this case, for a rock to win, it will win a scissors. A paper will win a rock, and then the scissors will win the paper, right? And so if we have something like win map of the P2 extends the player 1. So if sorry, this should be okay, this extends the rock, paper, scissors, right? So I'm saying, okay, so here, if we find based on the second element and what we get here, if it's the same as the first element, then we actually is winning. We say win, or else you'll be lose. say lose. So this is how we can get rock, paper, scissors. We get all pass, and then we hit submit. And yes, we did a good job of winning our rock, paper, scissors. So I'm quite curious about what are the other solutions that is possible. Let's see what ways people do. Okay, instead of defining map, you can hard code like you write it as a tuple instead, and if it's A-B combination extends the same tuple, then it's win or else it's lose. That's interesting, and see whether any other. I guess we can also create a map of all the draw and win and lose, and then we get the game rules to access the player 1 and player 0. I guess that's or you could combine both of them and then access as a map. I think that works as well. I think I'm fairly happy with what I've written here. This logic is like if it's draw, if it's the same as draw, and if it's in the win map, then it's win or else it's lose. I'm pretty happy with what I've written. So we've done day 17. Let's move to day 18. 1-8. So day 18, Santa needs your help to count the number of presents has to deliver. So these are the presents that we have. So count how many shoes that we have in this array. Okay. Got it. What we can do, I think we have come so far along that we know how we can solve this. I hope that you can see how you can solve this. What we can do is we're gonna recursively extract every element and then build an array whenever we find a shoe, and then we count the length of that array that only has shoes, right? So the idea is here I have toy extends array, and then we have item that we need to find, and what we need to do is toy extends infer the first and infer the rest, and if the first extends the item, right, then basically we've increment the array, right? Basically you need to increment the count, but we can't increment variables. We can increment array, and here we need an array, so let's say we write array, or the result extends any equals to empty array first. So we can increment by basically say first, okay, result, okay, increment. Okay, so we need to increment, and how we can do the increment is actually like something like result and increment by 1. But of course, after finding increment by 1, we still have to keep counting from the rest. So what we do here is that we will say we use count rest. I see. I'm not sure whether it's confusing for you guys, but let me just write it this way. So here, first of all, if it's an array that looks like this, firstly is when we extract the first one and infer the rest, we have to recursively find, right? So it counts the rest, the item, and the result. And once we couldn't find anything, I think this is at the end of the loop, the base case, where basically we can say the result length is the result that we want. Okay, so this is the final result. But of course, here we can't just keep going down the array. We have to know that we have to check whether the first is the item, and if it's the case, then we're gonna append into the result. So here the split where it says first extends item, And if that's the case, so if that's the case, then I will go down by saying result, add one more item to results. And if not, then we don't append to results. And I think that's it, right? So you have this is the case where we just keep going down the loop and we determine when to increment by appending to the array. And once we reach the base case, the end case of the recursive, we will return the value, the result, which is the result length of the result array. And you can see we have got a tick. All tests have passed. Let's hit submit. And good job! We've solved it. So we have cleared day 18. Let's move on to day 19. So day 19, the rebuild. So we're gonna rebuild. Okay, so this is given an array of numbers, and I'm gonna return this. Okay, so this is an array, a full-on array, but this gives us like two skateboards, one item, three item, three item. I think this number of items is basically based on the number of the value that we have. And I guess we need to we will start with skateboard and then BMX, scooter, surfboard, and loop back. So if the skateboard, BMX, scooter, surfboard, skateboard, BMX, scooter, and then continue and henceforth. Right, so that is something that we need to build up this array, and then this is a type that we need to return. Oh my god, this looks so complicated. How can we do this? But I guess we can start from the basics. We can start one by one and then figure things out. We can write something that we have already known so far, right? We know how we can build create array based on an item and a length, right? Item and a length, and then basically this gives us a result, right? Result extends any array. This we can create an array of the length of what we want. Let's say result length extends length. Then we return the result. Else create array item length and result with the item, right? So we are confident to create something like create array of this one with 4. We can confidently write this. This is something that we've been creating for the past few puzzles, past few challenges. So now we have this. The next thing is we need to recursively go through this array, right? So that's not that hard, right? Let's see. Let's think about this. So first is we rebuild takes in array, right? And then for the rebuild, what we can do is that let's see, from here, let's extract out the first element, right? So here array extends, infer the first, infer the rest, and when we hit the end result, then we will be returning result. So results is probably somewhere here. Result extends. So returning the results in our base case. And for here, what we need is with the first, we are going to create array based on something, and then this is the first And basically this is the thing that we just created from the array. What we need to do next is we're going to rebuild the rest of the array, where this one will add to the result. Right. Right. So basically like this. And so now our rebuild gives us all string because we haven't figured out what is the item that we're going to go through. For the item, what we can do is that we can start with skateboard like this. And so here we have our item. Pass item down, right? So here we have our item, but it's all skateboard. So whenever we go down one level, we need to know what's after skateboard, right? So we can have a map that looks like this. So skateboard goes to the BMX. The BMX goes to the scooter. And the scooter goes to the skateboard or surfboard. And the surfboard goes to the skateboard. So the next item actually can be determined like here. Just get the next item, right? Okay, this one, item extends key of next item. Just that TypeScript knows that this item is going to be the key of this one, and then you'll be happy to take it as a next type. And there we have it. We're able to rebuild this with rebuild the array. Basically keep going down the level, and then we get next item to index, get this one, and then this one we build on top of what we have learned so far, creating array out of items. And there we have it, a green tick mark, and I think we are great. Let's submit. And yes, good job. We have cleared day 19th, and let's move on to day 20. Day 20. Are you? Oh my god, what is this? Okay, so oh my god. Okay, so to ASCII art, we are gonna get a string. And I guess this one gives us something like Merry Christmas. So we're gonna draw ASCII art, right? We're gonna draw the art, like, so I think here we have already been prepared with all the characters that will be available, A, B, C, D, E, F, G, H, I. Okay, that's at least that's cool. And I guess this, so this we're gonna go loop through, and then we're gonna create this, right? And then at the end of it is we've seen a new line, then we're gonna split, and then we're gonna have like 3 more new lines, right? So I guess that's the idea of it. It's not fun, but I guess we can try do it, right? So first of all, we are going to have for ASCII art, the thing that we're gonna get is the string, right? And of course we need to have results, extends any, and I think we can keep 3 more variables to keep the verb as a variable for each of the lines that we're gonna draw. So that will be line 1 goes this one. So I'm gonna say it's string. Line 1, line 2, line 3. Okay, so let's start. First of all, we need to extract information. We're going to use conditional types with inferring. We're going to extract the first character out of the string. So what we can do is the string extends, infer the first character, and infer the rest. So if we can't do anything anymore, I think we reached the end of the array. Then we're gonna return results as the return type, and I think a result we probably will have to also append like line 1, 2, 3 as well. Remember to do the this is when we reach the end. This is where line 1, 2, and 3 probably has accumulated all the strings that we need. So this is the end base case. So for here, what we need to do next is that once we have taken infer, the first and the rest, we actually, what we need to do is we're gonna say to ASCII art the rest, right? The rest of the string here. And then also we have our results here. And then line 1, 2, 3 is probably based on what the first value is, right? So I'm gonna say the first extends the key of letters. Is it? I'm not quite sure. Let's see. For now, I'm gonna say letters. First, and then there's 0, 1. It's an array with 3 elements, so I'm gonna say 0. So here I'm gonna have like line 1 and this one, and I'm gonna move. We're gonna have like this, where this is line 2, first 1, line 3 is like the second element. And let's close this. Okay, so now the thing is that the first may not be the index of this one, right? And it's because it could be any other characters, right? So, but we know that wouldn't be the case because all the letters we know so far is definitely from here, except one character, except new line. So I think we can check whether it is that situation where if the first extends key of the letters, basically we know that if it's this, then we can definitely draw, right? And if it's not, then I think we know also for a fact that this will be a new line character. So we can actually say to ASCII art, where we have our rest, our result, and we're gonna start from new. So we're gonna have new line. Actually, we don't even need to pass in the line 1, 2, 3 because those have default value. But for result, actually we need to append this 3 to result. So basically very similar to what we have done at the base case here. Okay, so I think that's roughly it. Still not getting the answer, but let's see what we get so far, for now at least. Okay, I think what's happening here is that all these are capital letters, and when we have lower case letters, it doesn't really work well. So I think what we can do here is that we use the uppercase. Uppercase. Let's see. Is there? I think there's a utility called uppercase, right? Uppercase. Wait, don't just give up on me. Type A equals upper. I think there's too many things to compute. Let's upper case. There's no more hinting. I think the code editor just gave up. Let's copy everything and refresh. Okay, uppercase string, right? We can do uppercase E gives us capital E. So I think we can do that somewhere here. Let's see how we can change that. So here, uppercase first extends key of letters, but we also need uppercase like this, right? But it doesn't work. I think it doesn't pass in to tells you that this works. So one way we can do is we have to assign it to something else. And the way of doing that, right, is we can extract it to a different variable using infer. Okay, so for example, uppercase this one, right? It should be something like that. You can infer uppercase first, and then we use this uppercase first here instead. But uppercase first has to be key of letters. So actually we can also add constraints to what we can infer. So we say if this one extends key of letters, then basically this has to be key of letters, and then this will be correct, right? And so if uppercase and we infer it something out of this thing, and then the infer value, the character that we have, the uppercase of first, is matching the constraint of key of letters, then we go here, right? And therefore we basically is something that can find it here, and it also says it, and it's also uppercase, so we can access it and then we can draw it out, and that's basically it. We see the green tick, and yes, let's hit submit, and good job, we've cleared day 20. Let's go 21. Let's go. So I guess the puzzles has been getting harder and harder. I see we are playing tic-tac-toe right now. Okay, so tic-tac-toe takes in two types, the game and top center. I guess this is where I'm gonna place our piece, our state. So tic-tac-toe new game is okay. This is new game with an empty board and a state. So I'm gonna place X, I guess top center, right? So here. So this is what we need to return. The next board and the state of the board. Okay. Let's see. So we can place at top left, mid center, bottom left, and bottom center. And our state has to change to indicate who has won. So X has won in this case. We could also end up situation with, I guess, like O has won, or we end up with a draw. And there's also invalid states where basically, I guess this is like invalid move doesn't change the board and state. So we're gonna place something at top center again. This should gives us back to the same state, right? So this is from the same move. Passing it itself will get the same thing back again without changing a state. So maybe you're here in valid state, and then right before the draw. Okay, this is before draw. Okay, yeah. So this is invalid state will not change, and then we could also end up with a draw state. Okay. I would say interesting. Let's figure this out. I think the first thing that we can do here is that we let's define, after knowing the state of the board, let's define the next board based on the thing that we're gonna play, right? And then with that, we can determine whether it's winning, losing, and if so, what is the next state, right? So I would say like we maybe have a type that says next board, given a board that looks like this one, okay, and also a state or an action, or I would say move, extends. Move should be something like tic-tac-toe positions. Tic-tac-toe position. And also the chip that we're gonna play, right? So chip extends chip. Okay, so this one, the current boards, where we're gonna place it and what chip we're gonna place with, and that determines the next board moves, gives us the next board. So first of all, we have to extract and infer information from the move. So I would say move extends something like this over here. But we infer like y extends this one, and infer x over here. That has to be the constraint of this one. And if that's the case, then I guess we can move somewhere. And if it's not, then I guess move can never be something that's invalid. At least it's not based on what I see so far. It shouldn't be something invalid. If that's the case, okay, I think we can still return the board, right? And next, we need to, after getting the x and y, we need to place our board. Given an array, what we can do is actually we can use the map object literal to map the array into a new array. Okay, so for example, let's say I have like m that is taken an array, right? I can actually write something like key in key of array. Let's say just x, right? If I say type a goes m, array of 1, 1, 2, 3, you can actually see that this will maps the array into a new array, although this is like mapped object, right? And I presume, I guess like this is a way that TypeScript can handle, and it assumes like, I guess the key that is valid is probably like number index, and so that's why you can like loop it through, right? So so if I say like something like key, you can see that this gives me like 0, 1, 2, which is like the index of the array, but in strings. So but that's, I think it's useful for us right now. It's quite useful, I would say, because what we need to do is, after knowing the x and y, we are going to find out. I think based on x and y, we have our index, whether it's like 0, 1, 2, and then we can say like, okay, we're gonna map it where if it matches where we're gonna place our chip, then there is where we are gonna play the chip. Okay, so let's see. Here, first thing is gonna do the, I'm gonna know like where y and x will be in respect with the index, right? So I'm gonna have a map. I would say position, and this one, if it's top, the position is 0. If it's middle, I would say it's 1, and bottom I would say it's 2, and same thing as here, left is 0, center is 1, and right is 2. I'm just being lazy and keep all of them as one map. I mean, the key doesn't conflict with each other, so it should be okay. So here, move, I'm gonna map over the board where I have the index in key of the board, and I think first one is the Y position, right? So if index x, so index is a string, but this one is number. So what we can have is extends. Actually, we can just turn it into strings. Okay, so index extends position y, right? If it's this one, then we're gonna map through the array. If it's not, then I would say that nothing changed for that row, so we will return the board with index. And to loop through the array, we can actually have another type that does it for us. Map array. So we have a row, extends the tic-tac-toe board like row, and then we have the X position extends. We don't have extends. Okay, chip is this one, and this will basically, let's do the same thing again. Do the mapping index of row, and if index is position of X, X has to be something. Then we need to know whether we can place a chip, or else if here we're gonna return just row index. So here, whether we can place is basically if the if row index extends, if it's empty, right? Empty looks like this. If it extends empty, then I would say that yes, we can place it, and therefore we can place our chip. If not, I'm gonna say this is invalid, so I'm gonna return invalid as string, something like this. Okay, so that we know that it's, let me see, invalid. Yeah, so that we know that it's invalid state. Okay, so that we will, it's like a hint for ourselves, so that later on we don't have to change the state. Although the next board returns something, but that next board is an invalid next board. So here, what we have here now is that we will map array a board index X, and also our chip. And yeah, so we have our next board. So now let's go back to our tic-tac-toe. Tic-tac-toe is a game, extends. Let's see what's the game. Tic-tac-toe game. And also a move, which is this one, tic-tac-toe positions. And we can extract out the board and the state directly from the game, like basically say game extends board infer board infer state. This one has to be extends tic-tac-toe chip. This one extends the board, right? If the case, then we're gonna figure out the next board. If not, then I guess it's never, right? So this one gives us a board, next board, given the board. I think we also pass move and state. And the next state is, let's see if the next board, if it has anything that is like invalid, right? So I would say like if like number extends invalid. If it's invalid, then the state won't change. Then I guess we just return the same state. And if it's valid, then we're gonna move to the next state, right? So next state could be something like, given this current tic-tac-toe chip, we need to go to the next tic-tac-toe chip, right? So it's like, if the state extends across, then we're gonna return an O, or else we're gonna return a cross, right? So this gives us the next state, right? Let's see whether how far we have done. So here, I think this is correct. No more curly, no more errors. So we actually managed to get the next board and the next state. And for this move as well, we get the correct next board and the next state. This as well, I think we play well until we are reaching the end state of the game, because we haven't have any logic that handles the won case. There is also a situation with invalid states, invalid move. Okay, it seems like our board is wrong, and also the state is also wrong, right? Let's see what we can do here. I think instead of doing it this way, right? Because then actually the board shouldn't be the board. I think what we can do here is next board. Let's extract this whole thing into a variable. And to do that, usually we just do an extends infer a board. Like, okay, I'm gonna call it next, because next board is also, it's also like taken, board is also taken. I will just call it next. And if next, I will still think it's like something like this. Invalid. Okay, so sorry. I think we are a bit complex now. So infer next. So this one is just to make it in a variable, right? So infer next. We're gonna do something here. Do something. And if not, then I don't think whatever the case where it extends infer next with like that, it leads to nothing. So I'm gonna say never. And so whatever here we have, I'm gonna remove for now, and then we'll focus on what is the do something over here, right? So here we let's just indent, and so that you can see clearly, this one is here, right? And we're gonna do the question mark over here now. So here I think what we can do next is next number extend invalid. I think this one can extend a board, something like this. And if one of the value is invalid, then we will say that we will just return the same state, which is the game, right? If not, then I think our board will be the next, and state is something. State could be something like this one, right? Let's see if it solves, if it helps. How come this doesn't? Oh, this gives me all the time, which is a union. Union cannot extend this one. I think it's the other way around, where if this one extends the union, yes, then basically, yeah, now basically it works now, because invalid can extend like union of invalid and empty and something else. So this one gives me this one, which is correct. And now I think we need to handle the won case, right? So here we need to determine whether the board that we have has already won, or it's a draw, right? I think if it's a draw, it's easy. I'm gonna say like next. If same thing, this one. If like if we have any of the thing that extends, any empty cell extends like the union of all the value. If it's true, then I guess it's a draw. If not, then I guess we can move on to the next state, right? So this one, A. Oh no, sorry. If we have empty, then it should be like something like here, but or else it will be a draw, right? Yeah, so we handle the draw case, and so no more errors from here, and the other places are correct as well. I guess we just need to handle the win case now. So of course this logic over here, we can extract it somewhere, right? So that we don't have to keep like making this part of the code more and more complex. I think one thing we can have a type is called a let me have it here, type end state, and then given a board, like something like a any array. So this is the board extends, and then we need to figure out the end state, right? So maybe this should be considered as one of the end state. If extends this one is a draw. So if we still have empty spaces, then I guess we can figure out who have won. If not, then it's a draw, right? So how do you figure out who has won? One way is to get all the possible winning conditions. It's not a lot, but at least but I think it's, yeah, we can list them out, right? It's one, like it's horizontal 1, 2, 3, and then vertical 1, like like 1, 2, and then 3, and then the 2 more diagonal. So it's 1, 2, 3, 4, 5, 6 horizontal, and then 7 and 8 for the diagonal. So we have 8 different types of rows that we can check, And then if those are all zeros or all cross, then we know that if it's all zeros, then we know it's the 0 has 1. If it's all cross, then I guess the cross has 1, right? So how should we write that? I think one way we can write is we can let's assume we have another type like win, given a board like a row extends any, and so if the row, I wouldn't say any, but maybe 3 items, any. Okay. If the row extends something like, if 3 of them it's circle, then it's circle 1. And if it's something like this one, a cross, then the cross has 1. And if else, I think just ignore, so it's a never case, right? So we have win that gives us whether it's either this has 1 or never. And what we can do actually, one interesting thing about never is that we can union different multiple winning conditions, and never union with something else is just that something else. You know what I'm trying to say? Like for example, I have a equals to 1 union with never is just 1. Okay? And the trick here I'm gonna do is I'm gonna have win something, right? And win something else, right? All the different rows, and then it will just give me one of the thing. If all of them are never, it's just never. And if it's something, then I guess we get something as 1. Okay, so let's try that. Let's our end states. Who have 1? Well, let's see. Win. Let's see, row. So board 0, 0, board 0, 1, board 0, 2, right? Or we get 1, or we get 2, right? So this is horizontal ones, and then of course we have the vertical ones. So this is the vertical where 0 in front, like something like this. Okay, and also we have our diagonals. So we have 0, 1, 1, and 2, 2, and the opposite diagonal. So 0, 2, 1, 1, and 2, 0. Right, so this is our end state. So I can say that tic-tac-toe, where we have an end state, empty cell, and if it extends never. What empty cell? No, the next thing, if it extends never, then I guess it's not anyone who has 1, and also it's not draw. Then I would be sure that this is the next state that we will be, right? So this is a state, and if it's not extends never, then I guess we have our end state like this. Okay. Yeah, it is quite complex and complicated, but as you can see, we have our little green tick, and we have solved our day 21. Hooray! We've made it. So let's submit it, and pat yourself at the back because you've done a good job. Let's move on, shall we? To day 22. Let's go. So the day 22 is the Sudoku. Okay, so what you need is to validate a Sudoku. Validate it to say whether it's a valid Sudoku or not. So I think the return type should be true or false, whether it's a valid Sudoku. I guess it's similar to how we validate our tic-tac-toe, but we have to be a bit smart about it, right? Because how should we do that? Let's see. Okay, actually tic-tac-toe isn't that bad. So we have 9 rows, 9 columns, and then 9 grids that we need to validate, right? So 27 places to validate whether they contain all of them contains like all the types of things, right? And if it's one of them, it's not. If one of them it's false, then it's false, right? So we can have a right. So let's just validate one row, right? Validate row equals, so this is given as a row, and I assume this is in union of all the different types, and so validate row, and if the row extends reindeer, I'll say it's true. If it's not, it's false. Okay, and for validating a Sudoku, which is a Sudoku, which is a extends array. So it's array of array. And I would say the type over here could be, say, validate row. First one is I'm gonna get this horizontal row. So it is the Sudoku of the first element, and all the elements over here. So I would say it's like something like a number. Let me show you what I mean. Okay, so A equals to Sudoku. Hold on. Let me copy this whole thing. Okay, I'm gonna define something like get, and then Sudoku any array equals to Sudoku 0. So A equals to get this one. So if I get this one, I will be able to get the first row, right? Correct. And first row is, if I do the number, I'll get each array by itself, but union of arrays. And I think so in that case, I guess I need to do another number to get a union of the type of the element. So this is the first row. Okay, if I do like 1, then I get like the second row, but you can't really tell. Let me remove this. You will see that it is like It is the 1A. How come? One doesn't change even if it's 1. If it's 2, does it change anything? What is the array? Okay, hold on. This is the yeah, right? Second item is this one. Okay. Yeah, so second is this one. If I get fifth is the fifth row, right? Want to like the fifth row, and then I just get number to get a union of the array, and then number as the union of the elements, and then we should, if it's correct, it should get all of the different types. So if I just say like when I do validate, if it extends all the union, if it's the same, is all the unions of the elements can be assigned to a union of all the types, then I guess it's true. If not, it's false. So I'm gonna validate row for 0, 1, 2, the second row, third row, 4, 5, 6, 7, and 8. So we're gonna validating every row. And I guess next thing is we need to validate the column, right? So for the column, we can get into any number, but the column will be something like number 0, right? This gives us the column, because the number then gives us the hold on, gives us 0, 0. So this one, number and 0, should gives us this array, this array, this array, right? So it gives us all the first column array, and then the 0 should gives us the first element of the first column array, right? So I would say like something like this is column, this is row. So for the column, we have number 0, 0, right? And the third, I guess like we have also like this is the last row. But if I get something like 3, it's undefined. Or if it's like this is also undefined. But yeah. So we will validate from here like 0, 1, 2. And then we have 1 and 2. So these are for the columns. This is for the rows. And then lastly, we need the grid. So far, let's see what do we have. We have true. We have true. And we have situation with false where we still get true. Probably the grid doesn't, we haven't figured out the grid thing yet. These are all true for now. Hey, hold on. This should be false, but why is it true? Hold on. Type A equals to type B equals to true union with false. That's a boolean. Okay. So maybe that's not the way to return like type. Hold on, let me try this. Validate Sudoku, but only one of the column. This should give us false. Validate. This should give us false, but it still says true. Huh. Okay, the row. Okay, if it's only one item extends reindeer. Oh yeah, correct. I think it's the other way around. Extends. Yeah, this gives us false now. Yeah, this is correct. So if I do this and now do this gives us boolean instead of true. This gives us true. I think what we need to do is we need to in the end we need to turn something that's boolean to be false. Can be extends to boolean to be false, and anything that is only true is true, right? So I would say like I will call it a V. Okay, I'll just call it a V. And so type V value equals, if the value extends true, it's true, or else it's false. Right, so true false cannot be extended to true, but true can extend to true. So I think for the last case we get, oh no, still get boolean. Okay, let's see why it doesn't work. If I have, like, say q equals boolean, what does it give me? Oh, it gives me a boolean. Okay, it's a bit weird, but if I say true false extends true or false, yeah, it gives me false. So I guess there's something special when you do it. Is it with boolean? No, it's still false. So I think it's something special when you do it with generics, and it's certain thing it doesn't behave the same. I'm not quite sure whether it's a TypeScript issue, bug, or it's intended behavior. But if that's the case, then I guess like this whole thing, instead of making it part of a generic, I'm gonna say this extends true, then it's true, or else it's false. Right? Can we do that? Can we have that? Let's see. Yeah, in this case, this gives us false, which is correct. Then this gives us true. We still haven't write the case for grids, right? So I think what we need is for the grid. So the grid will be this, and this, right? Forms a grid. So this will be Sudoku for like 0, 0, 0, 0, right? This one gives me this thing. 0, like 1, 1 gives me this, right? No. Okay, so 1, 0 gives me this one, and then 2, 0 gives me this one, right? So I will need to validate, basically validate something like 0, 0, any element, and then union with 1, 0, union with 2, 0. Yeah, right. But why syntax error? Let's see, declaration. Let me just do some bracket and see whether it makes sense. Oh no, did I break something? Okay, this is valid. But if I say extends, okay, this is valid. Okay. So this is a grid. So we have the first grid. This cannot be a new line, is it? Okay, it's okay. We'll fix that later on. So here we have our first grid. We have 9 grids, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So first one is the 0, 0, 0, 0, 1, 0, and 2, 0, and then 0, 1, 2, 1, and so this is like 1, 1, 1, and here is the 2, 2, 2. And then we move on to row 3, 4, 5. 3, 4, 5. Hey, hold on. I think we have 3, 4, 5 like this. So I guess we can have the something like 3, 4, 5, 6, 7, and 8. And then this is 1, this is 2, this is 1, this is 2. Okay. Let's see what is not correct. Oh, so here we have 0, 1, 2, 3, 4, 5, 6, 7, and 8. Let's see. Validate row for the first Sudoku. This one is true, correct. This one is false. Okay, 8. 8, 2, 8, 2, 8, 2. Oh, hold on. This is 6, 6, 6. 7, 7, 7. 8, 8, 8. Right, this should gives us what does this gives us? Let's take it out. Oh, hold on, this is typo, this is 7. And without us knowing, I think we fixed a few typos, but the general idea is correct. The grid is 0, 1, and 2, and then row 3, 4, 5, row 6, 7, 8. And then we get this to get the union of all the elements in that grid. And without us knowing, we actually have a green tick at the bottom. We have already have our validating Sudoku. Let's save this one. And let's submit. And good job. We have solved the validation of Sudoku. Okay, so are you tired? You want to take a rest? And then we come back for day 23. So we are at day 23. We have solved a tic-tac-toe, a Sudoku, and now we are at the next game, Connect 4. Basically, this game is where you can slot chips from the top, where it files all the way to the bottom, and you try to drop chips at different columns of different colors, and the goal is to form 4 in a line, so 4 horizontal or vertical or even diagonal. My god, this sounds very difficult to do it in TypeScript. But this is similar to what we had for tic-tac-toe, so I guess we go for the same strategy. We're gonna go to find the next board based on the current board and state. And then with that, we are gonna move on to figure out what is the next state. And hopefully that's simple enough. I think what will be difficult is that in tic-tac-toe, it's quite simple to know who is winning, who is losing, or draw. But in this case, Connect 4, there's too many combinations that could be possible to figure out who is winning and who is losing. But we'll figure it out later on. So let's start from the beginning. So now we have a new game, and this is Connect 4. I think the first thing we can do is to create a type called the next board, given the current board, and the chips to put in. I'm gonna call chips. Chip extends Connect 4 chips. Next board extends any array. Okay, and let's see, board chip, and also the column to put in. So this is column extends number. So how do we know what is the next board? Well, we can let's see, we can do it. I think we can build the board recursively, right? Let's say, for example, if the board at length this gives us the okay, I think I know. Let's say, let's extract the last row and then try to see whether we can put a chip there. If not, then we're gonna extract the previous the second last row, and then we just keep doing row by row onwards. And then as we move out, we probably like trying to build up, save up the rows, and then we build up this whole map. I'm not sure whether explaining it this way makes sense, but first of all, we're gonna get the last row, right? So how we're gonna get the last row? We're gonna extract information, and how we do that? Use our same old trick, conditional types with inferring. So I'm gonna say if board extends. So this is the rest, and then the first infer the rest, and then infer the last row. Okay, and so if it's the case, then we do something. Okay, something. If not, I think let's just give up. Never. Okay, so here what we're going to do next is that if last row should be an array, right? And last row column, I'm going to check the column, extends a empty string, empty slots. If that's the case, okay, last row extends any. This one extends any. So if last row is something like this, which means we can actually build up the array. We're gonna put in the chip in this row, right? If not, I'm gonna look. Next part is the rest, chip, and column. Okay, but in that case, our board will just getting smaller and smaller and smaller. That's not what we want as well. that's not what we want, right? So what we can do here is that which means last row is something, the row that we can't put in any chip. So in the end, we want to put last row back so that we can create the final board. So what we do here is that we're gonna accumulate the rows, extends, and any. We start with empty array. So here we're gonna accumulate. So the last row and rows. So we're gonna put in the front. So later on over here, what this is, we're able to put chip in this row, right? Which means that what we're gonna have to return is actually the rest, and then put chip here. Okay, for this current row, and then the rows. Okay, so this is how we're gonna build up. Once we identify we can put something here, then this is the end of the recursion, where we have the rest of the board in front, and then we put chip here in this row with the chip and the column, and then the rows that we've just accumulated like this, right? So put chip here, we can define this one. Type put chip here, row extends any, chip extends this one, column extends number. So what we can do here is actually we can do a map by mapping, using map object literal by mapping through, and then find that if the current index is column, then we're gonna put this, or else we're gonna map back to the original value. So k in key of row, and then this is basically if key extends column, because key is a string, so we're gonna say we just turn it into a string with column. If it's the same value index, then I'm gonna say this is gonna be chip, else gonna be row key. Okay, so here we have this, and let's try it out. So for example, next board, as we put in this one with the chip. Let's say we put in this one, and 0 is the position, and A, what we get is, we can't really see from here. Okay, but I guess it should be correct, I guess. Let's try and put it into our connect for. So here, this is the board, extend any, and the column extends number. So here, first thing is this is not a board, the game extends. I think let's just put like this first, where game extends board, infer board extends any, and state infer state extends connect for chips. Then we're gonna have board equals to next board with the board state column here we're gonna say never, and then the state will be next states, right? So I will say like if the state extends the yellow, I will turn it into red. if it's red, I will turn it to yellow. So this will be like this. Right. And basically this, the first state has already, we've already passed this. This is correct. Although we can't really see what we got because it's collapsed, but this is correct state. This is even correct as well. So we managed to put on top over here. We can, this is true. This works as well. This works. And I think once we have something that is connect 4, we actually need to figure out who has won. Okay, so that's the next job that we need to do, is to figure out who has won so far. Okay, so here we need to, given a board, we need to determine what's the end state. Okay, given a board, extends any, we need to figure out what is the end state here. So let's say I'm gonna first write this first, end state, this one. And right now we are getting empty string, but we expect us to be able to figure out that this leads to the red has won. Okay, so we can check a few places. And how do we even do this? I think one thing we can try is that we can maybe we can form a string like this and then extends and see whether it's it has 4 things in one row, right? So for example, if I have something like this, let's say type winner. If I have a string, for example, okay, what I'm trying to say is that maybe if we can get, say, winner, something like this. Okay, and we should get red won. Okay, are we able to write a type that looks like this and gives us red won? I think that should be quite doable. I guess, I feel like maybe we can have something like extends, infer, something in front, and then we have 4 red circles, and then infer something at the back. I wouldn't say infer, we don't even need to know, so we're gonna say this is like some string over here, and if that's the case, then it's red won. And if it's for yellow, then yellow won, or else we're gonna say it's never. Oops. String extends. Okay, so here this what gives us red has won. Even if we have something spaces in front, this will still give us red has won. Even if this is at the end, this gives us the red has won. And if we swap it with yellow, something like this, yellow has won. Even you have red in between, have won. If I have something like this, never, no one has won. But if I have this, red has won. Okay, so we have this winner, and given the board, right, I think we can try to create like a union of all the winners for different rows. Okay, and with that maybe we can and then we can use that to determine like who has won. Okay, so for let's see how we can do this. I wonder whether if I have something like a union of, whether it will work with unions, like something like this. Let's see. And maybe put some space in between. Something like this. Does it work? Yellow has won. Okay, if I put space, no one won. If I do red like this, okay, so even with a union, wait, hold on. If this is on second, yeah, even with a union, I can still able to get who has won. So we don't have to get exactly the same string. We can get a union of the string, and let's see how we can get that. So first thing is we're gonna try to get the rows, right? Okay, so I guess I'm gonna write a get rows of the board. Is equals to okay, I will state the result extends any is equals to board extends, gonna do extract every row, and then for each row, okay, let's pause this here. So here next step is I'm gonna try to get winner, but then like turning this into the string so that it's much easier for me to determine whether who's winner, right? So if I get something like get row, I'll call it a row. Okay, I'm gonna call get row array extends any. So I actually want to have something like equals to get row. This one I want to make it into a string. Okay, so what I can do here is that I guess result is a string first, and then I will array extends infer for first. Okay, so if something that looks like this, then I can get row the rest, and here I can put the result and first. Extend string. Okay, something like this. Or else eventually the base case is returning the result. Okay, so I have something like this. So this one will form it in the string, get rows. Okay, it works nice now. And once we have get row, what we can do next is that if we're given a board, we can call this for board extends infer first row infer rest. Here we can basically, this gives us get rows board, no, the rest with the, we're gonna append all the results into we're gonna get row for the first row, and then append this into our result. Actually, this one can be anything, right? I feel like we can just be anything, so it's like a union of the result. And if we reach the end, we're gonna just return the result as the base case. So here, get rows. Let's see. Get rows of this one. Get rows. Will give us this one, a union of the different strings for each rows, right? So with this, right, we can actually, with this end state, one of the possible situations of end state is get rows of the board and call winner with this one for the rows. And this has already give us end state. This gives us the rate as 1. Okay. We can also have something like this one, and this should give us the yellow as 1. So we have been able to look at rows. Next thing is if we pass something like this, of course, by looking at the rows, no one has 1. So we're able to figure winning state by the rows. The next thing we need to do is we're gonna have a similar idea, but union for getting columns for the board and figure whether there's winner based on the columns. Okay, so for column wise, for column wise, let's see how we can do this. For column wise, type columns, get calls of the board extends any results. So for column, we have to go to we have to loop through column by column, row. Yeah, we have to loop through the column by column. What we can do here is that we can have the something like incrementer. Is it? Let me see. Okay, I know. First of all, is same thing as what we had just now. We will need a utility class called getColumn. So assume that we already know the column extends number. We need to get something from here, right? I think we probably will have like something like a result extends string equals empty string. Okay, so get column for this one with like 0. This should give us the string like empty, empty, red, yellow, red, yellow. Okay, so with this one, how do we get that, right? So here we can in same thing, we extract information using infer and conditional types. So board extends infer the first row, infer res. This one is an array. This one is any. So if we're able to do this, then we know we have to do something. And if we can't, I guess it's the base case, we just return the result. So here we are getting the first row column. This should gives us the string that we need. I think this can extend like this. Strings that we need. And then this should append to our result. So our result like this. Okay, so this will be our next result. I'm going to step into get column to recursively get to the rest. Okay, so get call, you see now we can get empty, empty, red, yellow, red, yellow. If it's 1, if it's empty, 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 yellow. If it's 2, then it's empty, empty, red, yellow. Right, so we're able to get column based on the column number that we're given. And now basically is that we can rely on this to get the results, okay, that we want. So we need to basically say, so now result is empty, right? So we can say get column result. Get column. Yeah, get column, the board, and then the result length. So basically get calls will give us the column for the result length, get call ball. This is a string now. Hold on, something is not quite right. Result length is unknown. Extends any. Oh, okay. This is wrong like this. Okay. This is just 0, right? So get call board. So this should actually give us the first row. Okay, so right now this is first row, but we can actually recursively calling this. For example, get calls board with this as the result. Right, recursively, then when we put something append to the result, then it's length 1, then we can get calls column of the first column, right? But this has to end, right? What is the ending state? Well, the ending state is when the result length is equals extends. There's no equals, but there's extends board 0 dot length. If it's an end state, we return the result. If the case, if not, then we return. Hey, hold on, why can't format? Return result. If not, then we are at the end of the get calls. Okay, so get columns will give us all the different columns that is available. Right? See? Right? The columns that's available. So if that get calls, we can again pass it to our winner state. Where's our winner state? Yeah, winner can be get rows and get columns. So here in our end states, let's see if we have situation that looks like a vertical winner. Is there a winner with columns? Okay, we don't really have, but we can create that ourselves. Let's say end state of this one It's okay, but if I put empty, then no one's winning. But if I replace this with yellow, then oh no. Let's see what goes wrong. Get call. Oh, this is an array. Okay, that's not what I want. We want to be making them as enum. So I'm gonna say like this. This turns into a union. Sorry, not enum, union. And then that should give us a union with get calls. Then the winner should give us the correct value. So here, for end state, this should give us the yellow as 1. I can do something like this and put a space here. Then red has 1, but if I put space here, then no one has 1. Okay, so I mean, of course, this is not a valid board state, but something like this would be valid, right? So no one has 1, but if we able to play until something that looks like this, then the red won. Okay, so we've considered straight, horizontal, but now we need to consider about diagonal. I think diagonal is the hardest, right? How do you even build the types diagonally into string? Yeah, how? So I don't know how. Let me think how we should go by. Maybe we can hard code something like this as a string. I'm not sure what the we can get the diagonal strings that looks like this. Let's see. Okay, so of course, first of all is type get diagonals board extends any, right? Diagonal has 2 directions. One is towards the right, one is towards the left, right? So let's say get right diagonal first. Okay, and I think as usual, we have a diagonals as plural that will give us all the diagonals, but there's also one that gives us diagonal, but at least we have some good starting point. And this good starting point, I would say that maybe we will have like a row extends number and column extends number. So for example, if I'm given okay, so let's say we're given the get R diagonal with this one and with say column 0, sorry, row 1, 2, 3, row 3, column 0, something like this. This should give us like the diagonal like this value plus this value plus this value. Okay, so I guess this one, of course, we need a result that extends like string equals empty string for now. And this should give us something like the board row column, right? This gives us a first cell. Okay, 30 is actually here, 30. the first cell, and should give us the next something like we should move, if it's right diagonal, the row should minus by 1, but the column should increment by 1. Okay, so we need something like increment and decrement, like increase, like given a number, and also decrease. Okay, to do that, I guess like one hack that we can do is we create an array of this v length, and then for increment we just add one more item and then get a length. For decrement is we get the array of length v and then reduce one item and then get a length. I guess that's the workaround for TypeScript, because we can't really say v minus 1, can't we? Can we? We can't, right? That's not supported in TypeScript. So here, first of all, is I'm gonna have like build array given v as, okay, I would say array length v extends number result extends any. And basically we can build this by saying result, do it recursively. So if the result length is equals to v, or extends v, then we can return the result. If not, we'll just recursively append to the result. So v result. Okay, so here we have given array length v. We just need one more item, so we'll say like this, and then get the length. Okay, so say for example type b equals increment 5. Okay, not b, c. Then you can see you get 6. And for this case, array length v extends infer, extends like this, infer res, then we get res length. Or else I guess we get 0, because if it can't be something like this, then I guess the length it's 0. So decrease 5 is 4, decrease 2 is 1, decrease 1 is 0. Okay, so decrease 0 is, I guess for now we just put 0. Wait, if we can't do it, then I guess it's -1. So okay, so we have increment and decrement. So with this one, what we can do is, after we get this cell, we are going to move up and to the right. So say get r diagonal, the board with row is decrementing the row, incrementing the column, and then this is the result. Here, like this. Okay. So the thing is now, why we get bored, this, and this. So now the thing is that this, we need an end state, or else it will keep recursively referring to itself. So what's the end state? The end state is we can keep moving up, up, up until the row is -1, I think. right? So row extends -1, then we hit the end state. There's also a situation where the column, we will keep hitting column, increasing column. Maybe like we start here, increment by 1, and then column is greater than the board zeroth length, right? So I guess it's something like I think I know. I will say row equals 0, then you can return the result directly, which is something like this one. And so when we hit row 0, then it means we can immediately get the result. And if we hit column extends board 0 length, then also we get the result directly. And then if not, then get diagonal, we're gonna board decrease, increase column. Okay. Increment column does not satisfy constraint number. What? This doesn't satisfy as number. How can that be? I guess maybe let's do something inferring. Extends infer new value extends. Yeah, so I'm gonna say that this infer something, a value of this one, which I have the constraint of number, and I just return number. If not, I guess if it's not number, then I just say never. So here TypeScript will know that this definitely returns us a number. So now we get R diagonal. Let's try R diagonal. What do we have for here? This will give us rate empty, rate empty. If we put like the fourth, then it will give us the yellow, empty yellow rate. And then if I get 5, you get the yellow, empty red rate, right? So I think it's pretty nice. Now the thing is that we need to get R diagonals for the entire board, right? So what does it even mean? Okay, so here, how do we even do this? I guess we start with 0, 0, and then we go. So I guess we have like the column extends number equals 0, row extends number equals 0, and we probably need somewhere to keep the result, so we're going to say result. For now, I would say extends any equals never. So I will start with 0, 0. So board, so it's like get R diagonal with board column row. Sorry, row column. Let's make sure that we have the same ordering. This is row column. Did I miss any apostrophe? Okay, I don't know why this looks like syntax error, but should be correct. So this one give us Hmm. I guess something stuck here. Let's copy this and refresh the page. Maybe something has stuck. Let's see. Let's restart the whole thing and let's see our R diagonals. Okay. Okay, this one gives us hmm. We start with row 0. How come we have the yellow, red, red? That sounds like this. Oh, hold on. This, we're not passing any of this. That should gives us, yeah, the starting one. Okay. And then this should, we should keep doing the get R diagonals until we reach the end. Let's see. Okay, so we're gonna, first of all, is we're gonna keep doing the get R diag. If row Okay, 0, 1, 2, 3, 4, 5. I would say a row extends decrement of board length, right? Board length minus 1. If row extends this one, we'll have reached here. Then we're gonna move to the right. So this is like get R diagonals board row column increment by 1 and results, or this one union with the current thing. I think a bit hard. Let's make this an array and then just append everything into the array. Right? Get R diagonals with an S. Ah, okay. I guess just now it's just like this should work. And then else, or else if row haven't reached there yet, then I guess we can increment the row by 1 first. Increment the row by 1 first, and then keep column as is. And I guess here we also need to check if the column has actually reached the end, which is column extends board 0 length. If it's reached the end, then I guess it's the results, else we're gonna be like this one. Increment the column by 1. So let's save this. And let's see what do we get. Infinite. Let's see. Let's copy this and refresh. Let's restart the server again. I think we probably have written far too complicated. Okay. Not too bad, not too bad. We hit some undefined here. Probably in our get R diagonal, this shouldn't be length, but okay, when we hit the length, I guess we just need the results like this. Okay. Still have some undefined here. Not quite sure, but I don't think it hurts anything. So we have our get diagonal, R diagonals. This we get R diagonals as like union of strings, right? If we have something that looks like diagonally a result, right? Something that looks like this. We have something 4 in a line. We can actually pass it to the end state to see who is the winner, right? So we have winner, get R diagonals for the board. R diagonals. Okay, I guess TypeScript is going crazy again. Let's refresh this. Shit. Okay, right? If this is something like this, oh, I mean, let's remove like this. So no one has 1, but if I add this over here, then the rate has 1. Okay, so you can figure out the right diagonal. So we actually need to copy and paste the idea, but put it as the left diagonal for getting left diagonal for our board checking. So here, let's see if the L diagonal, basically you can copy most of the code here, get left diagonal, but we start with something like, let's say, get L diagonal. If we start with 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5. Sorry, hold on. 1, 5, right? The 0, 1, 2, 3. I think we can have 0, 1, 2, 3, 3, 5. Then we start with we will decrement the row and decrement the column as well. And if the column extends 0, then we return. Okay, so here we basically get starting from 3, 5. Hold on. Row 3. Oh no. Row 5, column 3. Then we get yellow, red, empty, and also yellow. I need a yellow. So if it's L diagonal, if it's 0, then it gets this. The column is 0, we get this. Okay, let's see. Yeah, yellow, red, empty, yellow. Okay, so if it's 4, 5, then we get empty, red, red, empty, empty, which is good, pretty good. So now we have this get left diagonal. We're gonna get left diagonal with plural that give us all the left diagonals. Okay. So we have some starting point. I guess the starting point is with the starting with, let's see, we can start with here, and then we move towards the right, and then we move up, right? Something like this. So we start with the row, which is board length -1, and the column starts with 0. Okay, then we will first move forward with a not incrementing the row but incrementing the column, and then get the results. And once the column reaches the board 0 length -1, then we start to move up by the row. So this is decreasing the row, and if the row reaches 0 or like -1, then we return results. Okay, let's see. This one gives us, oh no, this one gives us, starts with this looks like a right diagonal to me, right? This this is like a right diagonal. I think we get, okay, so here we have to change this to left diagonal. So here we start with red, and then empty yellow, and then yellow, red, yellow, red, empty yellow, and then red, and then yellow, and then red. Yeah, it's pretty good. Okay, pretty good. So I guess we just plug the last thing in here. Where's our end state? End state, end state, where are you? So here we get our L diagonals. We have all the different diagonals and rows and columns with our end state. So let's just verify. The end state is the rate has 1. But if I have something like this, the yellow has 1. Okay. This is red. This is yellow. No one, the red has 1. Yeah, red with a diagonal. But if I blocked it here, then no one has 1 yet. But later on, if I do something like red, 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 and then we have a yellow, then yellow won because there's this diagonal over here. Okay, or the other way around where we have red, red, but this yellow it's not nothing, then we have red because we have a diagonal here. Actually, we don't even need this, right? Yeah. Or it looks like this would still win, right? Red diagonal win. So we have our end state written pretty nicely. Now go back to our board. We have the states. A same idea that we had last time. We firstly is we let next board extends something like a next, infer next, extends any. We get our next board like this. Okay. And then so this one we can replace to the board as next. And the state, we can get the end state based on the board. Extends never. If it extends never, then I guess it's distinct. If else we're gonna extend, then we're gonna have our end state as the next state. Save, refresh. I think it's a bit crazy, but yes, we have figured most things. I think one last thing we haven't handled is draw, right? In this case. So it's actually the same thing as end state. And state. Okay, so here, I think we can check if we have empty, tau, extends board number, then we find the winner, or else I guess it's a draw, right? Save this, then refresh again. It's a bit, sometimes I think TypeScript is a bit crazy. Yeah, because as it keeps reevaluating as we type, and then it's stuck in some infinite state. But now it seems like we have our green little tick over here. All tests has passed. Let's hit submit. And yes, we did a good job. We've solved day 23. So we left with 24 and the last day of Christmas. This Christmas comes early. I have no idea, but let's move on to the day 24. Hope that you are still with me. I know it's getting harder and harder, but this is almost the end. So let's see what we have for day 24. So here we are at day 24. Santa is stuck. Okay, let's see what we have. Let's see. Okay, so first thing is, okay, we have a maze with trees and spaces, and we have a Santa. And so, okay, I guess we need to define a type called move that takes in a map and gives us a direction. If it's going up, it has to go up. If it's going down, it will go down. But if it's stuck, if it can't move up, then it should return the same type where it stays at where it is. Okay, but if it can move down, for example, then it will move down. So you can move down, you can move left, but okay, you can't move left. But you can move left, right, down, left, right, and oh, okay, there's cookies. I guess if the Santa exits, so here when it's at the edge of the screen, and if it move out like left, then we get all cookies, which is the end state of the game. So I guess this is slightly easier than day 23. I feel, I'm not sure, but my sense is that how we're gonna solve it is we're gonna combine some of the things that we have done before. First of all, we're gonna find the position of where the Santa is in terms of the X and Y coordinate. And then given up or down, we are gonna calculate, we're gonna increment or decrement our X and Y coordinates. So that is done through what we have in the last day 23, where we able to implement increments and decrements. So we're gonna reuse that, and then we're gonna use that new position, trying to place Santa at the new position. If that new position is somewhat like maybe we had -1s or outside of the maze, like 0 or -1 or like greater than a leg, then I guess we will have to end up with all cookies. Okay, so let's try and break it down, and let's do that. So first thing is we're gonna have a few types. First is to find position given a maze. Extend maze matrix. Okay, so this maybe, let's say for example the position is 0 and 1. Then the next thing is we need to move find next position given the current position extends number and the direction extends directions. I think this is probably slightly easier. We can write it immediately now. So current position in extends, we're gonna extract what's the first and second position. That we can do with inferring, or we actually don't have to. Let's just infer let's just say direction extends up. Then we're gonna return a new tuple with current position. So I'm gonna say this is x and this is y. So this one is x will remains the same, and y will be decrement this one. Okay. So, and if directions extends down, then we're gonna have going incrementing the y position. And if it's going left, then I guess we will have decrementing here. And if it's going right, then we will have going to be incrementing here, the x position, and else it's never, okay? It can't be nothing. So of course we need to implement the decrementing and incrementing. Decrement and increment. So remember what we did last time, where basically we'll have first of all we create an array based on what's the value, and then we add one item or remove one item, and then calculate the length. Use that to infer the length, and therefore we can get decrement or increment. So first of all is make array given the length. The result is like this. So here, if result length extends len, then we return the result. Else result make array where len and result. Okay, and then for incrementing, value extends number. We will be making array of value, and we will be incrementing. We will be adding one more item like this one, and then we get the length. And decrementing is we'll make array based on the value, the length, and then with that I'm gonna infer the rest of the array. Infer the last item. Basically this is string, but the last item I'm gonna ignore, and what it is that it will be res length. And if it's array of nothing, then I guess decrementing it means -1. Okay, so let's save this. Let's just quickly try. Type A equals to decrement 5. This gives us 4. Yes. Decrements 1. This gives us 0. Yeah. 0. This gives us -1. Cool. Increment 0 equals to 1. And 9. This equals to 10. Okay. I think we have increment, decrement correct. And let's just try. Oops. So this is direction instead of directions. So let's try our find next position with 1 and 0 with up gives us 1, -1, correct. Going up, going down gives us 1, 1, okay. Going left gives us 0, 0, correct. And right gives us 2, 0, okay. So we're able to find next position. So we are slowly building up where the find position of the maze, and then we're gonna find next position of based on the current position and the direction. Okay, of course we need to define this generic, right? So first is the maze and the direction. The maze will be extents of maze matrix, and the direction will be extends the directions. Okay, so this will find us the next position. So this will find the current position of the center of the maze, and this gives us a next position based on the current position. And then we're gonna place center. Hold on. I think one thing we need to do is that this one we need to infer the x and y position. Infer x, infer y. And the reason why that is that we need to check if x we need to check if the x and y position is out of the maze. Maze x, y. Extends true. If it's out of the maze, then we're gonna build the cookie. Okay, let's just put a placeholder first. If it's not, then we're gonna, this one is the place center, right? And if it's not an array with x and y that can infer, then I will say it's never, it's not possible. So out of maze, type out of maze given x, y. I think what we can say is that a x extends -1, then it's true. Or if x y extends -1, again it's true. If x extends x extends the length of the maze. Okay, we need the boundary of the maze. I think we can pass in the maze directly to just get the boundary of it. Maybe let's put it in the first argument, like here. Extends maze 0 length. Then this is outside of the maze. This is also true. Or may y extends maze length. This is true, else it's false. Okay, so okay, we have this. Let's just quickly try this idea. Type A equals out of maze. Let's put a maze in here. And then -1, 1. This is true. Okay, if it's 0, then it's false. But if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if it's y is 10, it's true, right? 9, false. 0, 1. Yeah, okay. So we have this. Now we need to a few more types. Say for example, make cookie based on the matrix based on the maze matrix, what we can do is we're going to do a loop, right? So key in key of maze matrix, this gives us make cookie row based on, okay, we'll loop through, and this one will loop through maze extends this will give us key in key of maze equals to the cookie. So this one loops through an array and make every element map to a cookie, and then this gives this loops through every row and then loop through with the every row, and then each row will become make cookie row. This is okay. I guess let's see what we can fix here. Key as key extends number. Hold on, is it? It says that extends maze matrix like this, or is it just never? Okay, let's see. Make cookie, let's A equals to make cookie matrix with this maze. What do we get? Oh, what? Hold on. Oh, maze. This is maze. Okay. This gives us cookies. Okay, cookie. Okay, so that's correct. So this will be make cookie matrix based on the maze. And then lastly, we also have the place center with the maze, and then with the maze and the position X and Y. Right, this is extends the maze matrix. This is number. Same thing, we are gonna do the loop key in key of maze. So if the key extends if key extends Y, right, every row like this, because key is a string. If this extends Y, then we are going to place center for that row, maze key, or maze, I guess Y, with the X. Right, so if not, then we will be, if this row is not where we place, we actually might need to erase the center, or else there will be two center, right? We're going to place in this row, for example, and other rows, if we encounter center, we're going to erase that center. So we're going to say erase center row. maze key and X. No, yeah, like this. So first of all is the place center row. This extends the number, or like 0, like an X. Okay, so here how we're gonna place is key in key of maze, and key extends X. We are gonna place a center instead, or else we're gonna just keep whatever the original value of the in that maze position. And for erase center row, so this, okay, again, same thing. This could be something else. I guess we need the maze key extends maze matrix. Never. For erase center row, we are gonna take the row, and then if the maze key extends a center, then it could be empty. I'll just place whatever the maze key is. Okay, so here we able to place our center. So here we're gonna place our center, maze, X and Y. Extends number, extends number. Okay, so we're gonna place in our center, but don't forget we don't place our center easily if the position we're gonna place the center has a tree. Then actually we will have to keep as is, right? So for example, maze X Y, sorry, maze Y X extends a tree, then we can't place center. In that case, we just return the original maze, and if so, we can place the center. So I think we have everything now, except one thing that we have delayed until now to implement is find the position. Where is the position of center? Okay, so finding center, what we can do is, I think we have solved this in some of the days, but honestly, we have so many days passed. I can't remember where it was, but I think we can figure it out ourselves. So here, so the way of looping is we're gonna do a map, where we are gonna map, we're gonna create a map, use the map object literal, and then the value of what we are gonna map. So here, this is basically key of maze, right? So this, if we just map it this way, we're basically saying that we're gonna get an object, an array where where each of the value will just map to itself. But actually for this one, if we do the number, we can actually know what is the value of each of the row. And if any of this extends, or rather if a cookie a center extends this. So if there's one one of the cell has center, then basically this gives a union of center and something else. And sure, center will extend that. If that's the case, we found our center in that row, I would say that we're gonna find the X position of that center, right? So here for now I'm gonna say key first, which is that row, and if it's not, then I would say never. There's no center there. Okay. Of course, if we find the key, we actually still need to figure out the the x position of the center, right? So this is y. This key here is a string, so I think one thing we can do is extends infer y extends number. So this is y, and we need our x here somewhere. So yes, we're gonna find our position row of maze y, and this should gives us the x. So let's go find position row maze matrix number 0. So same thing, we're gonna key in key of maze, and basically here if the maze key extends or Santa Claus. So here is just one value, so we can extend Santa Claus directly. If you want, you can flip it over. I think it's the same. So if it's Santa Claus, then we basically found our x, but we also actually have to extract it out as numbers. So we're gonna say this extends this x extends number. If so, we're gonna return x. Also gonna say never. And this basically gives us, okay, let's try and show you. This gives us something that looks like this. Never, 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 never with 0. Okay. If we don't have Santa Claus at all, then this gives us never, 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 never. But this is an array. We just need to get all the values out, and a value we can get it by saying number. Okay, and so this gives us 0, and if it's nothing, then this gives us never, which is cool. It's okay. So it gives us number. So this gives us the x. This gives us same thing. This one is still an object where we can say number like this. This gives us the whole position. So I feel like we are there. Let's see. Like if I say a equals to find position with this map, then it's 0, 5, which is correct. Let's save this. Let's see where we got wrong. So okay, we're able to move up, down, down, left, up, right, down, down. Okay, so we're gonna move left. Okay, I know where we went wrong. So we just assume when we draw Santa, place a Santa, just put it like this, right? But if this thing, the original array itself already have Santa, we actually need to remove that Santa. So here, actually, we do one more step, is that if this extends Santa, then we're just gonna clear it, else it's maze key. Okay, save this, and you can see we have our little green tick, tells us all our cases has passed. We have moved our Santa correctly to where it should. We have solved the Santa in a maze, and let's hit submit. And good job, we have cleared this, which means we are left with day 25, which is the last day of Advent of TypeScript. And here we go. Oh no, it's thank you so much. It's just thank you. We have solved our Advent of TypeScript. Woohoo! Okay, so we have solved 25 days of Advent of TypeScript challenges. If you find this interesting, let me know. And thank you for following me through. And I'll see you in the next video. So don't forget to subscribe and hit the like button. Bye bye!